For over a century, astronomers have tracked Andromeda galaxy racing toward us at approximately 300 kilometers per second. The collision seemed certain. NASA even created detailed simulations showing our sky ablaze with new stars in 4 billion years. But a 2025 study by Till Sawala's team just flipped this cosmic certainty upside down. The chance of collision? 50-50, a coin flip rather than astronomical destiny. Picture the night sky transformed beyond recognition. Andromeda's approach would stretch across the heavens like a celestial hurricane, its spiral arms twisted into luminous ribbons. Stars would birth at rates unseen since the universe's youth, painting the darkness with brilliant blue-white giants. Yet this spectacular destruction might never happen at all. Vesto Slipher first detected Andromeda's approach in 1912 using spectroscopic measurements at Lowell Observatory, though he initially measured it as moving away before recognizing the blue shift indicated approach. For decades, scientists could only measure the galaxy's speed toward us, not whether it would actually hit. The Hubble Space Telescope finally solved this puzzle in 2012, tracking individual stars across Andromeda with measurements precise to within 5 to 17 microarcseconds per year. Roland van der Merel's team concluded collision was inevitable, spawning the popular Milky-Way merger scenario. Now, the European Space Agency's Gaia spacecraft has provided new data that changes everything. The story reveals how even our most confident predictions about cosmic fate can shift with better measurements. Whether Andromeda destroys our galaxy or passes harmlessly by depends on uncertainties smaller than a human hair's width when viewed from Earth. Imagine trying to predict where a bullet will land when you can only see its shadow from 1,000 miles away. That captures the challenge astronomers faced when measuring Andromeda's sideways motion through space. Determining Andromeda's true path required measuring its proper motion, how it appears to move sideways across our sky. This sideways motion proves harder to detect than approach speed because the distances involved are so vast. Van der Merel's Hubble team spent 5 to 7 years tracking individual stars within Andromeda to achieve their breakthrough measurement. They found Andromeda's tangential velocity was relatively small compared to its radial approach, with the galaxy following a trajectory that would result in collision. This nearly head-on trajectory made collision seem certain within 3.75 to 4 billion years. NASA's computer simulations showed the dramatic sequence: sky brightening from new star formation, 2 galactic cores visible simultaneously, final merger into an elliptical galaxy. The Milky name became popular in textbooks and planetarium shows worldwide. Astronomers described the event as our galaxy's ultimate fate, written in the stars themselves. But Sawala's team realized previous studies ignored other massive objects in our local group. The Large Magellanic Cloud contains 10% of the Milky Way's mass and orbits perpendicular to the Andromeda approach path. Triangulum galaxy, the third largest in our local group, also exerts gravitational influence on the system. These cosmic bystanders act like gravitational puppeteers, tugging on both galaxies as they dance through space. Using Gaia's improved measurements, Sawala ran 100,000 Monte Carlo simulations with 22 different variables. Results shocked the astronomical community. Only 50% of simulations produced collision within 10 billion years. When accounting for gravitational effects from neighboring galaxies, the probability of near-term collision dropped to just 2%. Till Sawala explained the uncertainty. We're not predicting that the merger is not going to happen, we're just saying that from the data we have now, we can't be certain of it. Galaxy collisions don't involve stars actually hitting each other. The distances between stars make this virtually impossible. If the Sun were a ping-pong ball, the nearest Andromeda star would sit 1,100 kilometers away. Instead, gravitational tidal forces reshape entire galactic structures over millions of years. The process resembles 2 hurricanes merging in slow motion, their spiral arms stretching and intertwining across cosmic time. When galaxies approach, they stretch each other into long tidal tails extending far into space. Gas clouds compress and trigger intense bursts of star formation, lighting up the merged system like cosmic fireworks. But the Milky Way-Andromeda collision would produce a relatively weak starburst because both galaxies have already consumed most of their gas. These mature spiral galaxies have exhausted their star-forming fuel, leaving behind stellar graveyards scattered with ancient red giants. The process called dynamical friction proves critical to the final merger outcome. As galaxies orbit each other, their dark matter halos interact and rob the system of orbital energy. This energy loss causes the galaxies to spiral closer together over billions of years until they coalesce. Think of ice skaters pulling closer as they spin. The galaxies accelerate while their orbits decay. At the center of each galaxy lurks a supermassive black hole. Sagittarius A star in the Milky Way contains 4 million solar masses. Andromeda's central black hole weighs between 100 and 200 million solar masses. These gravitational monsters would perform their own deadly ballet, spiraling inward while devouring surrounding stars. During merger, these black holes would eventually spiral together and coalesce, generating gravitational waves detectable by future space-based observatories. The collision would ring space-time like a cosmic bell, sending ripples across the universe. The final product would be a giant elliptical galaxy with unusually low central density. Our solar system would likely survive intact, but get scattered to the outer halo, more than 30 kiloparsecs from the galactic center. However, Earth faces a more immediate threat from our own sun's evolution. Solar luminosity will increase by 10% over the next billion years, triggering runaway greenhouse effects. Earth becomes uninhabitable within 500 million to 1.5 billion years, long before any galactic collision could occur. The Sun will boil our oceans and strip away our atmosphere while Andromeda still approaches through the cosmic void. The core uncertainty comes from measuring Andromeda's proper motion with sufficient precision across cosmic distances. Current Gaia measurements show improved precision in Andromeda's proper motion, but significant uncertainties remain in determining the exact trajectory. If Andromeda's sideways motion falls at the lower end of estimates, collision becomes nearly certain due to gravitational attraction. If the motion exceeds the higher estimates, Andromeda executes a flyby scenario, passing the Milky Way without merging. The large Magellanic Cloud's gravitational field effectively pulls the Milky Way out of Andromeda's direct path. Triangulum galaxy's gravity works in the opposite direction, increasing collision probability. These competing influences create the 50-50 odds that replaced previous certainty. The universe operates like a cosmic billiard table where every shot depends on forces we're still learning to measure. Sung-Mo Tony Son, co-author of the original 2012 collision study, acknowledged the new analysis represents significant progress. Sawala predicts that within 5 years, improved astrometric measurements could resolve the uncertainty. Mass estimates for local group galaxies also affect the calculations, particularly for the large Magellanic Cloud. Each refinement in our measurements shifts the cosmic odds, turning certainty into probability. Future gravitational wave observatories like LISA could detect supermassive black hole mergers if collision does occur. The local group contains roughly 80 known member galaxies that would eventually merge into the final system over 150 billion years. Whether called Milkomeda or something else, this merger represents ongoing galactic evolution through hierarchical assembly. The shift from certainty to probability demonstrates how astronomical science self-corrects as observations improve. Small measurement uncertainties compound dramatically when predicting events billions of years in the future. Scientists discovered that confidence and precision don't always align. Sometimes better data reveals how little we actually know. The Andromeda collision story reveals how cosmic predictions can shift from certainty to probability as measurements improve. What seemed like inevitable galactic doom in 2012 became a coin flip by 2025. This uncertainty doesn't represent scientific failure but the natural consequence of predicting events across billion-year timescales. Future space telescopes will continue refining these measurements, potentially resolving the question within this decade. Advanced astrometry missions could track stellar motions with unprecedented precision, finally settling our galaxy's fate. For Earth and humanity, the outcome proves irrelevant. Our planet faces extinction from solar evolution long before any galactic merger. Yet understanding our galaxy's fate provides insight into cosmic evolution and the grand dynamics shaping the universe. The cosmos operates on scales that humble human prediction. Galaxies dance to gravitational music we're only beginning to hear. Sometimes the most honest scientific answer mirrors that original coin flip. We don't know yet, but we're getting closer to finding out. The universe keeps its secrets well, revealing them only to those patient enough to measure twice and predict once.